starting soon. Yeah, okay,
All right.
thanks. Yes.
Yeah, so about the quantum ground state, all that stuff, I went back through the video as I said I would,
Yeah,
and I think I got it. Um, like multiple states having the same energy, but then because of the interactions, they get slightly different energy, and then
yeah,
we can separate them apart. Is the
yeah.
relevance of this that the third law becomes true again, like we haven't violated the third law or something like that?
Yeah, exactly. Yeah, the third law is basically so if we had, for example, like a bunch of particles which didn't have any interaction whatsoever, which is not realistic, right? And suppose they were all spin one, suppose there were like n such particles, and each particle had, say, spin one, then each particle would have three, three ground states, right? Because if in the ground state the particles had spin one, then the total number of ground states would be 3n, right? And therefore, omega would be 3n, and then s would be, k times, log of 3n, right? Which is not equal to 0. And so what this is saying is that at least the entropy density, as n approaches infinity, is 0. And what is happening is that because there are weak interactions, the Hamiltonian for each of this spin is no longer just the Hamiltonian that you had without interaction, but a Hamiltonian which is an interaction Hamiltonian. And because of the interaction of these, the way that spin interacts with, well, it can interact in many ways, but one of the ways that it interacts is through, say, magnetic, dipole moment. So if there is a magnetic dipole moment of effective magnetic dipole moment of all these other spins, okay? And what will happen is that we will get an interaction term which is a vector, and it'll choose out a direction in space, right? And that direction could be, say, in that direction, and that is, suppose we call it the z direction. Then the interaction Hamiltonian will be something which will have the z component of the spin one. And that means that for each of these particles, what will happen is that of the three, degenerate ground states, there will be a little bit of a splitting. So, and this will happen with all those particles. And of course, I didn't go into multi-particle problems because it's going to be very mathematically involved, but I just wanted to give you a flavor of how adding a symmetry breaking term lifts the degeneracy of the ground state, and therefore, the number of ground states reduced, and therefore, now the ground state, number of configuration in the ground state is much less. Okay.
Yeah, all right. Well, I think you said something about the entropy density tending to infinity or zero. I forget
Right,
which it
right.
was.
Because I mean, the thing is that the idea is that it's not the entropy density. That thing needs to go to 0 as t goes to 0 and n n goes to 0, right? So and so if for example
Sir, n goes to infinity.
yeah, sorry, n goes to infinity, sorry, yeah. So generically, thank you, Vijay. Generically, what happens is that the entropy is proportional to the number of states, because if you look at, we took a very very artificial system, but generically, the number of states is, if you have 10 to the power 23 particles, then, if you look at all the possible spins of these particles, if it's spin half, say, so it's even simpler than this problem, then this is going to be the number of possible configurations, right? So this is much more than, so this is equal to 2 to the power n. N here is 10 to the power 23, right? And so if you look at the entropy is going to have in it, it's going to be proportional to n, right? It's stuff, and then, some log of 2. So usually the entropy is basically, it scales with the n. So that's why, we are asking for the entropy density to go to 0 rather than the entropy. Because if our system is large, there could be, there is a chance that the entropy itself actually doesn't go to 0. Okay. So I see Moon is here. So let me just make sure she's given her. Anyone came in late that I forgot to?
Sir, I came like 5 minutes ago.
Oh, Ishik Hassan. Okay. Okay, good. All right. Is that all right, Saif?
So if the entropy density tends to 0, is that a notion of the entropy becoming somewhat very far apart?
No,
like
it's just
infinitely far apart or something?
No, it's just that entropy is an extensive quantity, right? The entropy density is like an intensive quantity.
I see. All right.
So there might still be, the thing is that if your system is large enough, there still might be some pockets of ground states which are far away from each other, right?
Oh, okay.
And that would be like a very technical way of violating the third law without violating the spirit of basically violating the third law. But so we want to keep the spirit of the third law, which is okay. So all right, any other questions? Okay, I see Raf.
Sir, I have a
Abdullah
question.
is here.
Abdullah Lafi. Yes, sir.
Yeah. Okay.
Sir,
Sorry,
I typed a question in the back channel.
Okay. Yeah. Can entropy of a system with particles in it ever be 0 in practice? Yeah, it can be. I mean, if all the, for example, if I take, well, we'll see that today, but for example, if I take a system of particles which has only, say a spin degree of freedom, right? So this is a particle with spin half. So we know that spin half, I mean, you don't have to know quantum mechanics, you just have to know the fact that it can be spin up each particle or spin down, right? So now the thing is that, hey, now look at the configuration in which everything is spin up. How many configurations are there of such type? Only one. So if you take the entropy of that energy state, that is going to go to 0, right? I see that Wajia is here as well, so let me change that.
This is because the particles are not indistinguishable. Is that the reason? They're all the same, basically.
Yeah, they are indistinguishable. Yes. Yeah, we are not bothering about. Yeah, exactly. Okay. Okay. Any more questions?